Okay, the lecture today is Eigenvalues and Eigenvectors. First of all, I have to discuss linear functions. Or linear transformation. Or matrix transformation. Okay, so if I have a vector space V and another one W, then a function from V to W is linear if two things happen. A, t of V1 plus V2, say, is t of V1 plus t of V2. So in a sense, it means that this t distributes over vector addition. If b t of some k times, say, V1 is k t of V1. Now, this top one is something that when students start learning college algebra, they most often make a mistake by assuming that most functions are linear. I guess it's like something which human brain does. Human brain does everything linearly, say. I don't know, but anyway. So let's see. If I have R1 as a vector space into R1, that's just simple functions. So these are like t of x is some function of x, right? And then x is just a number. Now in this situation, we consider that a vector. So that's the one-dimensional vector space. Now we want to see what functions from R1 to R1 are linear. First of all, let me ask this question. Now, one, there are some functions that students usually treat them as linear. The first one, which is the most common mistake, in my opinion, is this one, log. You might have made this mistake in college algebra. This is not log A plus log B. Remember? So log is not a linear function. Two, another mistake, it was square root. So, well, let me write here, so f of x log x is not linear. The second one is square root. So let's say you might have again made this mistake. You might have written this as a plus b. Or, in fact, it's not this. That's what you usually do. You distribute that square root over this addition, or here you distribute log over this. So fx, the square root of x, is not linear. Another one which I have seen students, that is squaring, say, or raising to some power. Well, this one is not a squared plus b squared, right? So f of x equals x squared is not linear. Another one which I have seen students very, not so often, this is the movie, the most, the first common mistake, say, or whatever. So the other one is this, which I have seen students sometimes. This is not 1 over a plus 1 over b. Now, what function is here? The function that I'm saying is not linear, is 1 over x. Is not linear. So basically, most functions that are, interesting in, say, in Calc 1 and Calc 2 that we studied are not linear. So let's see what functions are in fact linear. What is special about a linear function? So let me erase this and start with the t over here. So let's write t and let's write Rn to Rn. We know that this t, if it's linear, well, I can prove that, but let's just postpone that to some other time. So this t, in fact, corresponds to a matrix. This t corresponds to a matrix A, and that matrix A is an m by n matrix, right? So t of a vector here is a vector here, and that is in fact equivalent to writing A V equals W, right? So, and we can write this T as simply T of A, and this is what we call the matrix transformation. Okay? So, if T is linear from Rn to Rm, then it is a matrix transformation. So a matrix corresponds to that T, and it becomes a matrix transformation. So if we assume we know this thing, which is not hard to prove, then in fact we'll use these two to prove this fact. Now, what happened to a T which is from R1 into R1? So this T should correspond to a matrix which is 1 by 1. T should correspond to a matrix which is 1 by 1. Now, what is 1 by 1? It's just a matrix like this. So T should correspond to a matrix like this. Simply show some constant M. Or what is this? So what is Tx? T applied to X, which is matrix M applied to X, which is simply Mx. So the only linear function from R to R, or single variable, single valued function, the only linear, is in fact a function like this, Mx. So only this function is linear. Some students might say, okay, that's a line, I know, that's the equation of a line. Why I didn't add a b here, mx plus b? That's also equation of a line, but that is not a linear function. That's interesting, you can check that. You can check those two. So that's the only linear function in R1. So next time, don't make a mistake. I can safely say that absolutely no, or let's say almost no function from R to R is linear. So never distribute a function from R to R or a single variable function over addition. But anyway, now that was something aside to understand more about linear functions. Well, there are some interesting linear functions, things that you might not even think of. So let's let V and W be C infinity R. And remember, this is functions from R to R, which are infinitely differentiable. Okay? Infinitely differentiable like what? Like e to the power x, like sine x, like cosine x, and so on. So, let's take this function d. I will define what that is from C infinity R to C infinity R, and d of a function fx is simply f prime x. So d is in fact derivative. D is derivative. So let's check A and B. A. So if I have two functions d of fx plus gx, well, I know from Calc 1, oh, okay, well, let's write back. So this is in fact fx plus gx prime, right? And from Calc 1 we know that this prime distributes over this, so this is f prime x plus g prime x. And I also know that the second one is true, well, let's just check it, d of some constant k times a function x. We know that this is simply k of f prime. So this top one means that this is in fact d of fx plus d of gx. And this one is k times d of fx. So d, or derivative, is a linear function. A linear function from C infinity R to C infinity R. We can bring this down to, let's say, Cn to Cm or whatever. But for safety, I just took infinitely differentiable. So d is a linear function, or a linear transformation. D, let's just write linear, is linear. So derivative is linear. In the same way, any derivative of higher order, d2, d3, and so on, you can just guess what d2 means. That's f double prime and f triple prime and so on. You can easily, like this, prove that all of them are linear. The same way, we can say the same way dn, which is dn by dxn, is linear. Okay. That's the nth derivative. The same thing proves that it is linear. So linear functions are not just restricted to finite dimensional vector spaces like Rn. Because C infinity, we know it is not finite dimensional. In fact, any Taylor series, a function defined by a Taylor series, is in C infinity R, and that function is in fact generated by polynomials of any degree. So it is generated by 1, x squared, and so on. So it can't be finite dimensional. Okay, so now let's let T be a linear function from, say, Rn into Rn. So this is called a linear operator in R. If these two vector spaces have the same dimension, or the other one was also linear operator. So T is called a linear operator. Okay. So an eigenvalue problem is a problem like this. You ask yourself this: can I find a vector in Rn, say V, such that when I apply T to that vector V, it's like multiplying this V by some constant. So T V is like multiplying it by some constant. So you're asking this question: can I find a vector V in Rn such that when I apply T to this vector, it's like multiplying that vector by a constant? So what is given here? So if this is a problem, so let's say this is given to us and say find V. But it's not just finding V. What are missing here? So we are given, given T, fine. But as you see, there are two unknowns here. It's not just V, it's also lambda. Find lambda and V. Now look what happens here. Let me erase this top one and draw a picture for you, tell you what's happening geometrically. So, well, Rn, let's just say this is Rn, okay? And a transformation is given, or a linear operator is given on Rn T, and which means that both domain and codomain are Rn. So I can just picture it as one. So if T applies to something, I can just move it or rotate it or something. Anyway, so this vector is some vector here. B, say. I'm saying, I'm trying to find a V, a vector in Rn such that when I apply this T, you see a transformation or a linear operator in this case, if it's on Rn, it's like it's moving. It's like doing some, might do some translation, some rotation, something. So it's just changing this. So this vector should, maybe it rotates, maybe it just goes somewhere else, whatever. So it doesn't affect rotation. Rotation is more important. Whatever. So this is saying when I apply it to this, basically nothing happens to this vector. Basically nothing happens. Because it's just multiplied by some lambda. So when you multiply this by some lambda, what happens? It might get smaller, larger, or it might go this way. But its direction doesn't change. So this doesn't change the direction. And this A is not unique. This A is not unique. If I multiply this V by some K, so any multiple of V is okay. Which means any vector in this direction is a solution. So not just one vector, but any vector in this direction is a solution. Which again means that any vector in the subspace generated by this vector has this property. Not just V. Any vector in the subspace generated by V has this property. So in a sense, it's saying that this T doesn't change that subspace. That subspace is invariant. It stays the same. Nothing happens to that subspace. Anyway, so a problem like this is called an eigenvalue problem. So this is called an eigenvalue problem. Now, just an aside, this Rn and Rn, if I choose the C infinity say, and I choose D, for example, you can ask yourself, does D have, can I write D here and say dV equals some lambda V? Well, it's not this, it's for another course, in fact, a differential equations course, but anyway. So that also happens. For those operators also we can talk about eigenvalues and eigenvectors. Okay, an eigenvalue problem. And here lambda is an eigenvalue. So lambda is called eigenvalue. For an eigenvalue of t, and V is corresponding eigenvector. Okay. So before I continue, I just give you some examples. You might have seen this in your exams maybe, or maybe in problems that you solved. Without telling you that it was an eigenvalue problem, I have given you an eigenvalue problem. So let's start with some easy examples here. Same one. Well, let's take T to be from R2 into R2, and the matrix B. So matrix, let me write. Well, let's write some small numbers. So 1, -2, -2, say 3. And you realize I chose a symmetric matrix. There's a reason, we'll see why. So this T corresponds to A, or A corresponds to T. So the eigenvalue problem is this: A V equals lambda V. Okay? Well, I can move this A to the left-hand side, and this lambda V to left-hand side, and this is what some people prefer to take this to this side, some people take it to this side. I'm not sure what the book does, so let me take a look and see which one is. Okay, so it is the other way. I think it is left. Oh yeah, okay. So I can write this in this form: lambda V minus A V is 0, and that is 0 vector, right? And I can write this lambda V as lambda I. Now in this case it is I2, but in general some IN minus A V 0. So this gives me lambda I minus A times V is 0. Okay. So this is in fact the equation. If I solve this equation for lambda and v, I have solved the problem, right? Let's look at this. This is in fact a system of equations, right? A 2 by 2, in this case, a 2 by 2 system of equations. This is a 2 by 2 homogeneous system of equations. Well, I know that this has a zero solution. Any homogeneous system has one solution, 0, and we know that because of that it has in fact infinitely many solutions. Or just one. Yeah, it can be just one or infinitely many. So it has a solution. But I'm not interested in the zero solution. So when does this have only one solution? Well, if we go back to the theorems that we studied before, the system has only one solution if the determinant of this coefficient is not 0. Okay? So if the determinant of lambda I minus A is 0, then the system lambda I minus A V equals 0 has only one solution, which is V equals 0, 0. In this case, 0, 0 or 0. I'm not interested in this. So what? I'm trying to find, I know A times 0 is just 0. So any matrix or any transformation, not linear, any transformation that takes 0 to 0, which usually we assume it happens, does that. So I'm not interested in this. So the other way is this. Not, sorry, this is not 0. That is not 0. If that's not 0, then it has one solution. So if it's not 0, it has one solution. Sorry. So if it is 0, then the system has infinitely many solutions for V. Has infinitely many solutions. Has infinitely many solutions. Okay? So this one is what we want. The second one. I'm not interested in just 0 solution. I'm interested in infinitely many. Okay? So I'm interested in infinitely many solutions. So I made a mistake when I started. This should be not equal to 0. If this determinant is not 0, then it has only one solution, 0. If it's 0, then it has infinitely many. Okay, so let's go back to our situation. So let's erase this. Go back to this situation we have here. So an eigenvalue problem results in this. In fact, you can even start with this. You say, okay, I know I should write this, lambda I minus A should be 0. Now what does this give me? What is unknown here? A is given, so the unknown is lambda. Solve for lambda. Solve for lambda. Now, okay, let's see. Over there we have lambda I is basically lambda 0, 0, lambda, right? Minus A is 1 and negative 2, negative 2, 3. As you see, the lambda is in part of the diagonal, so lambda is in the diagonal terms are all lambda. So when you subtract, you will get this. determinant of lambda minus 1, 0 minus 2 is plus 2, 0 minus 2 is plus 2, and lambda minus 3. Okay? Equals 0. As I said, you might have seen equations like this without telling you that it is in fact part of an eigenvalue problem. But anyway, so we have to solve for lambda. Let's so with me, I don't have enough space here, so let me erase this thing and just. So the determinant is lambda minus 1 times lambda minus 3 minus 4 is 0. And that is lambda squared minus 4 lambda plus 3 minus 4 is 0. So I have lambda squared minus 4 lambda minus 1 is 0. Okay. Well, let me double check. Lambda minus 1 plus 2, lambda minus 3, okay, and then lambda minus 1. It's lambda squared minus 4 plus 3 minus 4, that is minus 1. So, this gives me lambda is 4 plus minus 2 plus minus square root of 4 plus 1, and that's 2 plus minus square root of 5. Okay, so the two eigenvalues are these two numbers. So let me write down here. So eigenvalue number 1 is 2 plus square root of 5, and eigenvalue number 2 is 2 minus square root of 5. So we are almost there. So we have found eigenvalues. So these are eigenvalues. Okay. So we have to find eigenvectors, the V. Eigenvectors corresponding to these two. So let's go back to this equation here. So let's go back to this equation. It was lambda I minus A times V equals. Okay. So we need this equation to find V. So let me erase this thing here and find the eigenvectors. So V is V1, V2. So let's say V is right here. So V is okay. So lambda I minus A is in fact this. So I have this equation. Lambda minus 1, 2 lambda minus 3 times V1, V2 is 0, 0. Okay? So this is the equation that I should solve for and find V1, V2. Well, if I have a 2 by 2 matrix, and if I set this determinant equal to 0, it means that this matrix, the two rows are not linearly independent. So I have to just solve one of them. It means that the two equations